So welcome to Unit 8. This is the first in a series of 8 sessions. So we're going to start off with assignment 1, and we'll look at the first part of assignment 1. We've split the sessions into 2 to cover each assignment. So that's why there's 8 sessions altogether to cover the 4 assignments. So what we're going to look at today, first of all, just to tell you briefly what we're going to do. What we'll do, we're going to calculate the distribution of a bending moment and shear force diagrams, and then we'll look at the stress due to bending in a relatively simply supported beam. And following that, we're going to look at the governing equation that allows for the selection of an alternative standard roll steel section for a beam or a column. Yeah, so that's really the second part of the assignment. That's task 2. So we'll start off with task 1. Just to tell you how it relates to the learning outcomes and the assessment criteria. So this session is going to address assessment criteria P1, and that comes in the form of activity 1 and task 1. And also we'll look at assessment criteria P2. So these are past criteria. And in that, we're going to justify the selection of standard roll steel sections for beams and columns. So they're the assessment criteria, and that's covered in task number 2. So the question we're going to look at, and the approach is going to be all the way through, is that we'll do examples, and by doing the examples, that'll actually get the theory over in the same vein. So we'll start off with this example. So we've got a 6 meter long beam. It's a rectangular beam, 5 centimeters by 10 centimeters. Supports the loads as we've shown in the diagram below, in the figure below. And for the beam, we need to determine, first of all, we need to determine the reaction forces. Secondly, the expression for the bending moments for each section of the beam. Now, that's very important that we focus on that, because that's probably going to be the most difficult part of what we're going to do. And then the last thing, we'll draw the bending moment and shear force diagrams. So what I'm going to do now, I'm going to share the screen with you so we can actually work through that example. Just give me a second to do that. Okay, right, so you should have that question on your screen at the moment. So I've put some of the text in, I've put some of the drawings in just to save us a little bit of time, because we don't want to spend time drawing it, using your valuable time just drawing the question. So that's our question, and we've got a beam that's loaded from the left-hand side to the right-hand side. So we've got a reaction at A, and we've got a reaction at D. And we've got point loads at point B, and we've got a point load at point C. And also we have a distributed load along the length for 3 meters from point C to point D. So with these questions, always the first thing to do is to try and find the reaction forces RA and RB. Now, the thing to remember, if this system is in equilibrium, that means it will be in equilibrium, otherwise it would move. Then the sum of the forces in the Y direction must equal 0. And similarly, the forces in the X direction must equal 0, but of course we haven't got any forces in the X direction on this case. We need to set a sign convention. Now, it doesn't matter which way you do the sign convention, so long as you don't change halfway through the problem. So the norm is to accept that, and we'll have vertical forces, and we'll call them positive forces. And then any downward forces, we'll give that a negative sign. So that's our sign convention. Now, providing we stick with that, then we're not going to go far wrong with this question. So if we start doing the summation of all the forces in the upwards and downwards direction. So first of all, we'll start from right to left, from left to right. And that's usually the usual way of doing these questions. It doesn't matter though, you can go either direction, as long as you don't change halfway through. So we'll start off with RA, that's positive. So we've got a reaction force RA, and that's positive. The next force is at point B, and that's down, so that's going to be minus 12 kilonewtons. The next one is at point C, so that's going to be 8 kilonewtons. We've also got to bear in mind this distributed load, and that's also acting downwards. So it's got a weight acting down here from that point in that direction. That's always considered to be at the midpoint of the length of the distributed load. So the force down is simply, it's negative because it's downwards, and it's the distributed load, which is 4 kilonewtons per meter times the length, which is 3 meters. But also we've got a reaction at D, and that's acting upwards. So we're going to add to that reaction at D. And for equilibrium, all that must equal 0. Now that's a relatively straightforward sum, so I'm not going to do through the maths. So we'll have RA plus RB. Sorry, RD, that's a D. Let me rub that out and write it again. RD, and that's equal to 32. Okay, so you'll see there we can't find the reaction forces from that equation because we've got 2 unknowns. So we need to do something else to find the values of RA and RD. So what we do now, we're going to take moments around either point A. So we can take moments around point A, or we can do moments around point D. Now it doesn't matter which way you do this, so long as you're consistent. The normal convention is to start from the right-hand side and do the moments in towards the left-hand side. So we'll do that. So we'll take moments about D, because I've written that in anyway. And also, again, if the system in equilibrium, the sum of the moments around D must also equal 0. I'll just change my pen back to black. So what we'll do now, we'll take moments around point D. Again, we need a sign convention. So we're going to put the sign convention in. So if it's a clockwise motion, we'll give it a positive sign convention. And if it's an anti-clockwise motion, we'll give it a negative sign convention. Again, it doesn't matter which way around you have the sign convention, providing that you're consistent. But this is the sort of customary way of doing the sign conventions for moments. So we'll start off from D. The first moment is going to be the force acting upwards, RA, and at a distance from D, which is 6 meters in this case. So we'll have RA. I'm going to multiply that by the distance, which is 6 meters. And because that's acting upwards, that's in a clockwise direction around D. So it's going to be positive. The next force is the 12 kilonewtons, and that's acting in the opposite direction. The moment is in the negative direction, so it'll be minus the force, which is 12. And that acts at a distance from D of 5 meters. So we'll put 5 in there. And likewise with the next force, which is 8 kilonewtons, and that acts at a distance of 3 meters from D. Now we come to probably the more awkward part, is that we've got to consider the distributed load. Again, it's acting downwards, so it's going to be negative. Now the load is going to be 4 times 3, that's the force acting downwards. But where it acts halfway along the distributed load. So it acts at a distance here. And if we look at that, sorry, I messed that up. Let me rub that out and tidy up again. Bear with me. I've got quite a bit of rubbing off to do now, haven't I? Go back to the pen. Right, so the force acts down. We assume it's at the midpoint. So it acts down from that point. And that's at a distance of 1.5 meters. So it's multiplied by the distance, which is 1.5 meters. And that is equal, again, it's going to be equal to 0 for equilibrium. Now you'll see what we've done. We've eliminated RD from our equation. So now we can actually solve for RA. By taking moments at that point D, RD doesn't create a moment around that point because it passes through it. There's no distance. So it eliminates RD from the equation. So we end up with a calculation. We can determine the value of RA. So if we do the sums, RA is equal to 17 kilonewtons. Now we've got RA, we can go back to what we developed previously. We know RA plus RD, is equal to 32. We now know RA, so we have 17 plus RD is equal to 32. So RD, and therefore we can calculate there will be 15 kilonewtons. Okay, so we've done that bit. We've found the reaction forces. So now what we need to do is to go on to look at the bending moments in each section of our beam. And it's important we take time to do this properly. Now, I want you to understand what the bending moment is. We're going to take an arbitrary point, X, along the beam between A and B. So that's our first section, A to B. We know RA is 17 kilonewtons. So I'll write that down so we don't forget. So that's 17 kilonewtons. And we write RD, which was 15 kilonewtons, just so we don't forget. But what I want to do, we're going to create this artificial point and we'll give it the label XX. So we're going to take moments around that point where the line XX is drawn. So what we can do, first of all, if we look to the right-hand side, so if we do moments on the left-hand side, then from X, the only force we have is the 17 kilonewtons, and it's at a distance X. So the moments to the left-hand side is just 17 times X. Then if we do moments now on the right-hand side, so we do moments on the right-hand side. Now it's a little bit more complex, it's a little bit more fiddly, but we'll take our time. So first of all, if we look to the right of our artificial point X, then we have a force of 12 kilonewtons. And of course, that's causing a clockwise rotation, so it's positive. So we'll have plus 12. And that acts at a distance of, well, it's 1 from A to B minus the distance X. So that would be 1 minus x. And see, it gets a little bit fiddly here. So you've got to be careful how you determine the leverage or the distance from point X to our point B. So we've done now the 12 kilonewtons, so we do the 8 kilonewtons in exactly the same manner. Again, that's causing a clockwise rotation. So it's going to be plus, it's going to be 8 kilonewtons again. And that acts at a distance of 3 meters from C to A, less the distance X to get to that point there, to get to this point. So it'll be 3 minus X. We've also got another force, which is the distributed load. Again, that's acting in a clockwise manner. So it's going to be plus, the load is 4 times 3. We've done that before. Yeah. Now, this is where we've got to be careful. Where does it act? Now, it acts at midpoint there. So it would be the midpoint of our mass distributed load there is 4.5 meters away from A. So it's times 4.5 meters. And again, we've got a minus X away from that term. And of course, we mustn't forget now our reaction at point D. So it's minus this time because it's an anti-clockwise moment. So it's minus 15. And that leverage there is 6 meters minus this distance X. So it's 6 minus X. So that's the moment on the right-hand side. Now that looks a bit messy, but what I want you to notice, if we tidy this up and and multiply the brackets out, what we'll end up with is minus 17x. Okay. So what that tells us is at our point X, we know our beam is going to be sagging at that point. And this is our point X here. Draw that very well. We've got a moment to the right-hand side of 17x. And we've also got a moment on the left-hand side, which is minus 17x. What the temptation here is to say, so the total moment at our point X would be 17 twice, but that's not the case. Now, the reason that that's not true, I want you to think about a situation. So if I have a beam, a straight beam, and I apply a load of 10 kilonewtons in that direction, and apply another load of 10 kilonewtons in that direction. So the temptation would be to say, what's the total load on that small beam? And you'd say the tensile load is 20 kilonewtons. However, it isn't. If we were to draw that again, so we'll draw our beam so it's not drawn very straight, and we apply 10 kilonewtons in that direction. But I anchor this to something, so that can be anchored to a wall or something. So now if we looked at it, you would say that the load on that beam is 10 kilonewtons. Because what happens is the wall provides a reaction force of 10 kilonewtons in this direction. Yeah, and likewise with the moments where we have 17 x kilonewton Newton meters going in the clockwise direction, we have minus 17x going in the anti-clockwise direction, but that's a reaction force. Now, because this is sagging, the sign convention is to say that we use the positive. That's a positive bending moment. So if we have a sag a sagging beam, then the bending moment is positive. And if we have a hogging beam, then the sign convention is negative. So that's something to bear in mind for when you do the last assignment. Right, now we're in a position to start working out the bending moments for each section. So just continuing with this one at the bottom of that page. So the bending moment for section AB is simply 17x. Because it's going to be in a sagging condition, it's positive. So MB is 17x. Now we need to move over to the next section of beam. So now we're going to look at section B to C. And again, we're going to put an arbitrary X value, X point between B and C. So the distance from our arbitrary point to the reaction at point A, we're going to call that X. So that means the moments to the right of that, X, position X, M, and we call it bending moment BC. That's going to be equal to, and let's see what we've got. Well, first of all, we know RA is 17, so I'll just write that into reminders. So it's 17 times X, but also, and that's clockwise, so that's positive, but also we got the 12 kilonewtons, which is acting anti-clockwise. So it's going to be minus 12, and that's going to act at a position of X, our distance X, minus the 1 meter to get back to point B. So it would be X minus 1 in that case. And we can tidy that up. So that becomes, if we work that out, becomes 5x plus 12. So just bear that in mind for the next page. So now we're going to go over onto the next page. And we're going to do exactly the same process again. We're going to find the bending moment. Again, we've got to put an arbitrary position for X in that section CD. So we'll call that X again. But this time we've got two loads. We've got the 8 kilonewtons and we've got the distributed load. Now the distributed load is a bit more fiddly, so we've got to take a little bit of care with that. So the moment for section CD is equal to, now we'll start off at the distance from X, we've got RA. So it's 17 times X. So as reminders, put 17 in there, kilonewtons. Again, minus 12 for the second load at point B, because it's anti-clockwise rotation. Again, that acts at X minus 1. So that's the same as before. Now we take the 8 kilonewtons. So again, it's causing an anti-clockwise rotation. So it's going to be negative. So it's going to be minus 8. And the distance from X to C is going to be X minus 3. Now we come to the awkward one, the distributed load. Again, we know the load, we know it's causing an anti-clockwise torque, so it's a moment, so it's minus 4. Now, we're only considering the load to the left of our arbitrary point X. So we only need to consider this part of the load. Yeah. So that distance from X to C will be X minus 3. So that's that distance from our point X to point C. But where does it act? Now, this is where you can easy to make a mistake. It's now going to act halfway along that distributed load from X to point C. So it's going to act at that point there. And we get that. So we're going to multiply that by the leverage or by the distance. And that's actually going to be, again, it'll be distance X minus 3. So that gives that distance there, but we need to go halfway along that. So we divide it by 2. So we can tidy this up a little bit. So that's going to give us a moment in section CD, which is going to be minus 3x. So that's just tidying this equation up. Plus 36 minus 2, and that's going to be times x minus 3, and that's going to be all squared. So that's our expression for the bending moment at any point distance x along that section from C to D of that beam. Right, now we're in a position, we've done the hard work now, so all we've got to do is to make sure that we can plot the bending moment diagram. So if we look at the 3 terms, first of all, look at section A to B. The bending moment was 17x. So what we do is we go to our bending moment diagram, and if his x was equal to 0, then the bending moment would be 0. So I'll draw that in a different color so we can see it. So when x is 0, the bending moment is 0. Remember, this only applies for section A to B. When the distance is 1 meter, so x is 1 meter, then the bending moment will be 17. So that's going to be, we'll call it there for now. So that's going to be 17 Newton meters, kilonewton meters. And we can join those two together. And the expression for that is simply 17x. So we could plot that in 0.1 of a meter, and we could, that's the profile you get, because 17x is a straight line. The next section is section B to C. So if we look at B to C, it's 5x plus 12. So if we plot that between the values of x is equal to 1 and x is equal to 3. So if we put x equals to 1 in that expression, we'll find that it actually gives us a value of 17. So when x is in section BC, using the expression of, I'll write it in, shall I? Is it 5x plus 12? Let's write that in there. So we'll have, the expression is 5x plus 12. So if we put x as 1, so it becomes 5 plus 12, which is 17. So that's going to give us that point there again. Now, if we put the next value in, if we put x equals 2 meters, because there's no loading in between, and calculate that, we'll find that comes out at around 27, I think it was. So we'll do that now. So that's 27. So that gives us that point there. And again, we draw that line between the two. So the last bit is to put our final section in, section C to D. Now the expression is a bit more complex. So you've got to put values of x in between 3 meters and then the second one at 6 meters. But it's not a straight line in this case. So if we put our value of x as 3 meters, you'll find again, you come out at 27. So that will end up at that point when x is equal to 3 meters, m will be equal to 27. Now, if we put x equal to 6 meters, what we should find is that the bending moment will be 0. So that'll give us that point there. Now, if you were to do it for different values of x, say x is equal to 4 meters, 5 meters, and so forth, you'll get a plot that looks a little bit like this. I'll start that again. It's a bit messy. Let's see if I can draw it a bit better. So it's a curved line that gradually drops off to the 0 again. Again, it's not the best line in the world, but it goes back to 0. And the function of that line is what you calculate, what you determine for section C to D. That's the bending moment diagram done. The last bit of that question was to work out the shear force diagram. Now, if we look at the shear force diagram, we'll set off at, we'll use a red pen to draw the shear force diagram. So we've got the reaction at RA, which is 17 kilonewtons. So that's going to go up by 17 kilonewtons. So that's going to be our shear force at A. So I'm going to draw that again, just to tidy it up a little bit. So that's the shear force at point A, and that's going to be 17 kilonewtons. Then, because there's no other loading between A and B, we draw a horizontal line across from A to point B. Now what we have a downwards force of 12 kilonewtons. So it comes down 12 kilonewtons. That will bring us down to 5. So this is going to be 12. That's going to down to that point. So that will be 12 kilonewtons in the downwards direction. And that'll leave us at 5 kilonewtons. We then go to point C, which is a horizontal line across. Again, no loading in between, so we just draw a straight line. And this time we've got a load of 8 kilonewtons. Again, that's in a downward direction, so we'll draw that down. And that's going to go down by 8 kilonewtons. So that's going to be 8. And that will bring us to our point here, which is going to be minus 3 kilonewtons. So now we're on the last part of this exercise. Now, because you've got a distributed load, what we should do now is that we know we've got a final force at point D, which is 15 kilonewtons. So that's going to go up from minus 15 up to, God blimey, back up to the original. That's going to be 15. This is minus 15 kilonewtons. And we simply have to join these two together. Let's see if we can draw a better line this time. No, not having much luck tonight, I'm afraid. So we're nearly finished with this part of the question. Let's scroll up a little bit. And we're going to join those two together. So we'll go from there. Oh, I'm getting worse at this. Let me just draw that once again. Yeah, okay, thanks. That's gone now. So let's try that once more. But it's a straight line anyway. So we'll draw a straight line from there to there. That's a straight line. Okay. I'm afraid it's not that straight, but anyway, that's you get the idea. Now, if you want to check whether it's right or not, the area above the line, above the 0, must equal the area below the 0. So if we just do a quick check to see if we've got it right. So we've got 12 times 1. So that area is going to be, 17 times 1 is 17. The area of this section is going to be 10, because it's 5 times 2. So that's going to be 10. And if we work out the area of the last section, that's going to be minus 15, minus 30. So that's going to be minus 27. But it's an area, so it can't be negative. So it's going to be 27. So we can see we've got 27 above the line and we've got 27 below. So it's correct. And there's no more you can do. You know then you've got it right. So it's almost like a self-checking that you've done everything correct. So you know that you've done that absolutely correct at the moment. Right, the last part of the question was to find the stress of the surface. Now, if you look in the notes, you'll see an equation where you have the bending moment over the second moment of area is equal to the stress over y, and y is a distance from the neutral axis to any point in that cross-sectional area. And the higher stress will always be at the surface, the furthest distance y away from the neutral axis. Now, because this is a rectangular section, the neutral axis goes through the center of area. However, if it was a bit more complex, then you have to, if it was a complex shape, you'd have to determine where the neutral axis is by working out the centroid of area, but that's a different exercise altogether. So for this one, we're told it's a rectangular section. We're given the height of 1.1 meters and it's got a width of 0.05 meters. So the furthest distance from the neutral axis is going to be 0.05 meters. Our bending moment equation or bending equation, we're trying to find out the stress. So we want the stress. So that's what we want. So we don't have that. But what values do we have? Well, we have the distance to the surface, y. So it doesn't have to be to the surface, but that's where the higher stresses will be. We have the bending moment because you've just calculated the bending moment. So you can work out the stress at any point by just applying the bending moment at the particular point that you're concerned with. We also need something called a second moment of area. Now, what we need to do, we need to calculate the second moment of area. Now, this is part of the assignment. So just give you this is a little bit of a heads up on how to deal with the assignment. So first of all, rearranging that equation in terms of stress, we get the stress is equal to the bending moment over the distance from the neutral axis over the second moment of area. Now, the second moment of area for a rectangle, I, is simply b d cubed over 12. Now, you're not expected to remember that in any way. You would always have to look that up in tables. So that is given, that's a standard equation for bending moments. For different shapes, there's circles, etc. have a different I value. So that's for another unit. But at the moment, that's the second moment of area for a rectangle. So now we have our value of I. We have our distance y. So at the point of maximum, if we want to find what the maximum stress is, we'd have to go back and find where the maximum stress occurs. And if we look at our bending moment diagram, we see that the maximum stress occurs at that point there, at point C. So that's where our maximum bending moment is, and that's 27 kilonewton meters. So all we have to do now is to work out the stress at the top surface or at the bottom surface, it doesn't matter. We can work out the stress is equal to 27 times 10 to the 3 times the distance y, which is 0.05. And we need to divide that by our second moment of area. So I'll just do the second moment of area for you. Second moment of area I is equal to B, the breadth, which is 0.05, times the depth, which is 0.1 cubed. I'm going to divide that by 12. So the second moment of area is 4.1667 times 10 to the minus 6. So it's a small value, and that'll be the units of that are meters to the fourth, because if you look at it, you got length meters and meters cubed, so that gives us meters to the fourth. So we're going to divide that by the second moment of area, so it's 4.1667 times 10 to the minus 6. So that will give us a stress in the order of 320 megapascals. Sorry, 32 megapascals. 220 megapascals. Right. On the top, that stress will be negative because it's in compression, but it'll be a tensile stress at the bottom. So it's going to be compressive at the top because it's sagging, and it'll be a tensile stress at the bottom. Likewise, you can get the stress distribution through that whole unit, and it'll look something like this. If you look at the stress distribution, we carry the neutral axis over. The stress distribution will look something like that, where you'll have the maximum compressive stress at the top and the maximum tensile stress at the bottom. Okay, now, one thing I want you to notice about that equation. So if we've now got stress is the bending moment times y over the second moment of area. Now, one of the questions, the second task is to find an alternative beam to the square beam. So you're going to replace this rectangular beam with an I-shaped beam. So how do you go about that? So how do you look for an alternative beam? Now, the key to this equation is if you look at the values of y over I. So if you're going to change the beam, first of all, what will happen is that the bending moment, if you keep the loading the same, the bending moment will be the same, so it won't change. So the only thing you can change is the depth from the neutral axis, and you can change the second moment of area. So if you have an I-beam, so that will have an I value, or whatever here. You'll also have a neutral axis, and you'll have a distance y from the neutral axis to where the highest stresses are, either the top or the bottom. It doesn't matter, one's negative and one's positive, so that'd be minus y. So all you have to do is, when you look through tables, standard sections of universal beams, they will actually publish the value of the second moment of area. So that'll usually be published, so you don't have to calculate it. It's quite difficult to work out the second moment of area for an I-beam. But because you've got, it's published, what you've got to do is look for values of y over I for your new beam, your alternative beam, and you want to try and keep them the same as you had for the original rectangular beam. And that's the second task in activity 2. So it's to find an alternative beam. Now, you won't do it first time. You'll have to try a couple of different size beams until you get a value of y over I is similar to the original rectangular beam. And then that's your justification for the replacement beam. So replace the rectangular with an alternative I section beam. Right, so I'm going to stop sharing this screen. I'm going to go back to the presentation slides. Where's my mouse gone? And we'll go back to the original slideshow, which is that one there. We're sharing that now, and we'll move on to the next slide. So we'll put all of these points up. So this is really a resume of what we've just done. So first of all, determine the reaction forces. First thing you must do always is to determine those forces, otherwise you can't do anything. Then you divide the beam up into sections between each load point. So we had A to B, B to C, and C to D. Then you need to develop the bending moments expression for each section. So remember, we had for section A, we had 17x, and for section B, B to C, we had 5x plus 12. And then it was a bit more complicated for the last section, C to D. So once you've determined those expressions, it's simply a matter of plotting the bending moment diagram for each section for the corresponding values of x. And that's it. Last thing is to plot the shear force diagrams by looking at the forces and their direction and plot them on the shear force diagram. So the second task was to look at finding an alternative beam to replace the existing beam. So you start off with the bending equation, which we've just done. So we rearrange the bending equation. So you get stress is equal to the bending moment times distance y, which is the distance from the neutral axis to wherever you want it in that section, but you always do it to the top or the bottom surface because that's where the maximum stress is going to be. And you divide by the second moment of area. And I've reiterated this point here, providing that the loading scenario remains unchanged, then the bending moment profile will not change. Yeah, so that's important to remember that. If you don't change the loading conditions, then the bending moment profile will remain exactly the same. So that term will be constant, the bending moment term. So the only variables are the distance from the neutral axis to the surface and the second moment of area. So when you're going to select an alternative beam, try to ensure that the value of y over I is the same or slightly larger than that for the original beam. If it's slightly larger, it means the only thing that will happen is the stress will be slightly smaller, and that's not a bad thing. So this will ensure that the stress levels at the surface will be the same for both beams. They might be slightly less if your value of y over I is slightly bigger. So if you've got any questions, we'll stop recording now. And if anybody's got any questions, if they can